All right, for homework 29, we're starting just by matching some graphs. Honestly, a lot of this assignment is like pre-calc stuff, reminding you how inverse functions work. So it says match the graph of the function with the graph of its inverse function. The inverse functions are A, B, C, and D. So I know that I realized the screenshot of the book that I took this from was written in. So these answers are correct, but I will kind of explain. Remember, when you are graphing a function and its inverse, the graphs are reflections of each other across the line y equals x. So that means, like, if you have a graph that looks like this, the inverse function, hop that across this line, will be something like that. So it's a very rough sketch there. So for example, and they have reciprocal slopes. So like for the linear functions, how do you know b versus c, whether that's 9 versus 10? So this slope here is -6. So the inverse slope will have to be -1/6. So that's why those two go together. And then here the slope is 1. It goes up 2 over 2. And so the inverse will have, what's the reciprocal of 1? The reciprocal of 1 is 1. So they're not opposite reciprocals. They're not perpendicular, but they do have reciprocal slopes. Okay, so what else? The other ones are kind of easy, I think, to pick out, like D, reflect that across the line y equals x, it will have to look like 12, and A will have to look like 11. So, so these are the correct answers. Yes, C, B, A, and D. But I just wanted to kind of talk through that. All right, number 26 says, find the inverse function of f, and then graph both f and f inverse on the same coordinate plane. Describe the relationship between the graphs and state the domain and range of f and f inverse. Okay, so how do you find an inverse function? You switch the position of x and y in the equation, solve for y. So we'd have to add 1, take the cube root of both sides, call it f inverse. So f inverse of x is equal to the cube root of x plus 1. Part B was graph f and graph f inverse. So we need to remember about our parent functions and their transformations. So the x cubed graph normally starts at 0, 0, but we're going to shift it down 1. The next 2 points from the center there are over 1, or right 1, up 1, and left 1, down 1. And then from the center, right 2, up 8. From the center, left 2, down 8. So this is my graph for f. And then f inverse, I guess I switched my colors here, but f inverse is the cube root of x plus 1. So the cube root of x graph also normally starts at 0, 0, but this has been shifted to the left 1. Its points also go right 1, up 1 from center, left 1, down 1 from center. And then it's the cube root. So from the center, it's to the right 8 and up 2, and to the left 8 and down 2. And these graphs should look like a reflection across the line y equals x, which they do. Remember, another way to check things is like, for example, I have the point 2, 7 on this graph. So on the inverse, I have to have the point 7, 2. And that's working for all of the points here. Part C was describe the relationship. So f and f inverse graphs are reflections of each other across the line y equals x. And then part D was find the domain and range. So these functions are not very exciting. The domain for f and the range of f are both all real numbers. It's a cubic function. It's polynomial. And then same with an odd root function. Its domain for f inverse and the range for f inverse are also all reals. One thing I want to remind you of from our pre-calc days are, remember, for when domains and ranges are restricted, you're checking that the range of f matches the domain of f inverse, and the domain of f should match the range of f inverse. Did I just say that same thing twice? Anyway, the diagonals here match, so we always checked that in pre-calc. Okay, for this problem, use the graph of the function f to make a table of values for the given points. Then make a second table that can be used to find f inverse and sketch the graph of f inverse. Okay, so make a table out of these points to begin with. So x and f of x. So the points that are plotted for x are 0, 1, 2, and then they skip a point at 3 and they go to 4. And then the function values at those points at 0 are at 1, 1 is 2, 2 is at 3, and 4 is 4. So remember the relationship between f of x and its inverse function are that you just switch the coordinates, so the outputs become the inputs for the inverse. So the outputs of f become the inputs for the inverse, and the inputs for f become the outputs for the inverse. And if we plot those points, here's 1, 0, here's 2, 1, 3, 2, and 4, 4. So again, remember there should be this line. Mine's a little wobbly, but there should be this line that's going across y equals x. That's the line, like their axis of symmetry there, their reflection axis. All right. Use the derivative to determine whether the function is strictly monotonic on its entire domain and therefore has an inverse function. So first, let's talk about the domain of f. For any natural log or log function, the domain is that the expression inside of the logarithm has to remain positive. So x minus 3 needs to be greater than 0, which means x should be greater than 3. Okay, and then how do we use a derivative to determine if something is monotonic, which means always increasing or always decreasing? So if I can show that the derivative is either always positive or always negative, that means that f is strictly monotonic. So I'm going to find f prime. So f prime will be 1 over x minus 3 times 1, because it's times the derivative of x minus 3. The times 1 doesn't matter, but I just want you to get in that habit so that if the derivative is something other than 1, that we remember to chain rule. And then, yeah, we're thinking about the sign here. So if we plug in anything higher than 3, then x minus 3 is going to remain positive, right? Like if you plug in 4, 5, 6, whatever. So for x values greater than 3, f prime of x will always be greater than 0, always positive. Therefore, f of x is strictly monotonic. In this case, f is always increasing. Therefore, f has an inverse function, so yes. Next question says, delete part of the domain so that the function that remains is 1 to 1. Remember, 1 to 1 means the function that remains has an inverse function. Find the inverse function of the remaining function and give the domain of the inverse function. There is more than one correct answer because, well, there are actually, no, there are all kinds of correct answers. I'm going to split this right down the middle. So you can use a half parabola, but really there are infinitely many answers because you can say, I'm going to say, let f of x be x minus 3 squared, and let's just let x be greater than or equal to 3. But you could cut it off anywhere. You could say greater than or equal to 4 or 5 or whatever, anything that would pass the horizontal line test. So any other section of this parabola besides 2 that are on opposite sides of 3 here, so you can't pick 2 to 4, for example, anything that would cause it to pass the horizontal line test would make it 1 to 1. So I'm going with this. Okay, so that's my first part. Find the inverse function. So if we switch x and y to find the inverse function, solving for y, so this would change to like y is greater than or equal to 3. So when I square root both sides, I technically get plus or minus radical x. But I need this to stay positive because I have a greater than here. So if it's a negative, then when I add 3 over, I'm not going to get values that are less. I'm not going to get values that are greater than or equal to 3. I'm going to get values that are 3 minus radical x. So that's not going to work. So if this is greater than, you choose the positive. And then add 3 over. So 3 plus radical x equals y. So the inverse function is radical x, and then plus 3 is outside of that function. So there's the inverse. Give the domain of the inverse function. So 2 ways to get domain. It's a square root function, so x needs to be greater than or equal to 0. Or also remember that the range of f becomes the domain of f inverse, right? The outputs of the original function become the inputs of the inverse. So same thing here. If I look at 3 to infinity, the y values that are greater than or equal to 0 in the original mean that the x values will be greater than or equal to 0 in the inverse. All right, so that's that second part. For 73, it says verify that f has an inverse, then use the function f and the given real number a to find f inverse prime of a. All right, so there are steps to this, but first it says verify that f has an inverse. So the domain for f is all real numbers. So we want to make sure this isn't one of those cubic functions that does this, where it would like fail the horizontal line test. Let's assume we don't have a calculator, so I don't really want to graph this. But I can quickly find f prime. That's 3x squared plus 2. And then for any x value that I plug in, 3x squared is going to be positive. Plus 2 will still be positive. So this is for all x values that are real numbers. F prime of x is always greater than 0. So that means that, therefore, f is 1 to 1 because it's strictly monotonic. Okay, so there is an inverse function. Now, you're not supposed to, you're not really supposed to like find the inverse function because that would be hard to do, right? Switching x and y. You're not supposed to find the inverse function and then take the derivative of it. What you're supposed to do is first figure out like, okay, I know that f inverse prime of a, even though that's 2, I know it's the reciprocal of the slope on f of x of its like corresponding point. So we always start by saying we're not going to plug 2 into f. We're going to set f equal to 2 and solve for this. So let's get this equal to 0. Now I can't factor, but I can kind of guess and check. I'm limited to the factors of 3 if you're not sure about guessing and checking. If you plug in 1 plus 2 minus 3 does equal 0. So x equals 1 is the solution to this equation. So what does this mean? It means that the point 1, 2 is on f, and that means that the point 2, 1 is on f inverse, and it means that their slopes are reciprocals of each other. And so in our notes, we said by definition, that means this. Because I can't just easily find an f inverse equation, if I want to find f inverse prime of 2 here, that's going to be equal to 1 over f prime of this point, so f prime of 1. Because I can't find the f inverse equation. If I could, I would just do that. But if I can't do that, then if I want to know what's the slope at this point on the inverse function, I go back and say, all right, well, it's the reciprocal of the slope on f at this point. Okay, and we already found f prime. F prime was 3x squared plus 2. So this is 1 over 3 times 1 squared plus 2. So the answer is 1/5. Right? And double check that. If you plug in 1, you get that f prime of 1 is 5, right? So 5 versus 1/5. If we were to graph those, we would see that those slopes are tangent at each of the points. Okay, let's try this again. So same idea. First, we want to prove that this is 1 to 1. So for x values greater than -1, we're checking this out. So let's find f prime, because I guess I probably could sketch this, but I don't really want to sketch this. Excuse me. So let's find f prime. So low, d high, minus high d low over low low. This is just x plus 1. This is just minus x minus 3. So the x's cancel. You get negative 2 over x plus 1 squared. And remember, you're just considering, like, what will this always come out to? So, okay, x value is greater than negative 1. Whatever you're plugging in here to this denominator, you're squaring. So that's always positive. So you're always going to get negative 2 divided by a positive. So for all x values greater than negative 1, f prime of x will always be less than 0. So therefore, f of x is strictly monotonic, and it's 1 to 1. So an inverse function does exist. All right, now my next step then is to say, all right, well, let's figure out what point we should be plugging in here, because we want to find f inverse prime of 2 again. And we know that's equal to 1 over f prime of what? We have to figure out what the what is here. So set f of x equal to 2 and solve for x. So I'm going to multiply the x plus 1 over, distribute the 2 through, subtract x to the right side, subtract 2 to the other side. So x equals 1 again. All right. And then we already have an f prime equation. F prime was here. So negative 2 over 1 plus 1 squared. Let's just flip this around. So 2 squared over negative 2. So I got a slope of negative 2. All right, number 85. Find dy dx for the equation at the given point. All right, so we can't easily solve for y, so we're going to use implicit differentiation. So take the derivative with respect to x of both sides. The derivative of x is 1. Derivative of y to the third is 3y squared, and we have to chain rule, dy dx. Minus 14y, again, dy dx, plus 0. So if we factor out a dy dx, we would have 3y squared minus 14y. So I'm just going to divide that parentheses over. So that equals dy dx. And then we're supposed to evaluate dy dx, evaluate at the point negative 4, 1. Which remember is an xy coordinate. Now our dy dx is only in terms of y, so this is just going to be 3 times 1 minus 14 times 1. So negative 1/11. Right, for the next problem, no calculus on this one. It just says use these two functions to find the given value. So this is just composition. And these are equations that we are able to switch x and y and just easily solve for. So let's go ahead and do that. So x equals 1/8 y minus 3. So you'd be adding 3 and then multiplying by 8 to get y by itself. So f inverse of x is 8 times x plus 3. And then if g of x equals x to the third, switch x and y, you'd be taking the cube root of both sides. So g inverse of x is just cube root of x. Okay, now remember what your composition means. So this means g inverse of f inverse of negative 3. So that's g inverse of, plug negative 3 into f, and you get 8 times negative 3 plus 3. So that's really just g inverse of 0. Plug 0 into g, and you get the cube root of 0, which is 0. All right, and then our true or false section. Remember, you should always just try to be thinking of counterexamples. So determine whether each statement is true or false. If it's false, explain. If f is an even function, then f inverse exists. So remember, even function means y-axis symmetry, like the classic case is the parabola. So this fails the horizontal line test. It's not one-to-one. So no, that's not true unless you restrict the, you would need to restrict the domain. Domain must be restricted. It's not that you can't find an inverse relation. It's that you can't find an inverse function. The inverse that you come up with would not be a function. So that's the difference. If the inverse function of f exists, then the y-intercept of f is an x-intercept of f inverse. That one's true. Because remember, all that's saying is, let's just make something up. So let's say you have a y-intercept of 0, 5. Then remember, you're supposed to flip all of your x and y values. So the x and the next on the inverse, the point would be 5, 0, and that is an x-intercept instead of a y-intercept. If f of x equals n to the n, where n is odd, so we're talking x, x cubed, x to the fifth, x inverse exists. And it's only this one term. It's not plus a string of other terms. So that one is true. And I can kind of prove that one. If you think about it, f prime of x would be n times x to the n minus 1. And remember, n is guaranteed to be odd. So an odd minus 1 will always be even. So if n is positive, then you're going to get a positive times an x to an even. So that'll always be positive. And if n, even if n is negative, like if it's x to the negative 3 or something, you'd have a negative times an always positive. So that'll always be negative. So f prime of x will always be positive or always negative. And remember, that was our requirement to say, oh, that means f will always be increasing or always decreasing, and then therefore strictly monotonic or one-to-one. There exists no function f such that f equals f inverse. So this is false. Now, I understand if you're having a hard time coming up with one like this, but even just like y equals x is an example, right? That's one-to-one, and that has an inverse function. But the one that I thought of was, or the one that I'm used to looking at teaching is if f is 1 over x. So if y is 1 over x, if you switch those positions and you solve, you still get y equals 1 over x. So yeah, so that's another example. Or yeah, just like y equals x, then x equals y, and those are inverses of each other too. All right, that finishes this homework assignment. Like I said, it was kind of light on the calculus work. Homework assignment number 30 is a bit longer and a bit heavier in the calculus too.